fundamental law of classical physics. We talk about something you don't usually learn in the physics class and physics textbook. They don't talk about this. What is the fundamental law of classical physics? Okay. The candidate here is fundamental. The definition of fundamental comes from the force. Okay, and there are two different forces in the classical physics, which is gravity and Coulomb's force. This is a force between charge, and Newton's gravity is force between mass. Okay, so are they fundamental law? Well, this Newton's law is an interaction between two mass, direct interaction. Okay, so it doesn't say anything about how quick they interact. As soon as you put another mass, it's within 0 seconds they start interacting or not, and you have to evaluate every mass between mass. The force is the same situation for the Coulomb's force. You have charge and how quick they interact and stuff. Okay, now classical physics evolved from those very crude form of the fundamental law into the so-called Poisson's equation. And what is this triangle? Triangle is a second degree derivatives. Basically, it's a inverse triangle square, and that means okay, so here the mass create the field called potential field. Okay, the charge create a potential field, and this potential field interact with particle. Say you have a mass, this create a potential field, and potential field is going to interact with this another mass. The same thing happen. You have a charge, create a potential field, and that's interact with another charge. So it's not direct interaction, but interaction between field. This create a field, and this create a field. So the charge for the Coulomb's force and the mass for the Newton's gravity create a field, and the field interact. So that's is evolved classical physics. So you have to learn the field theory, and the field can be vector. So this vector calculus become prerequisite for college level physics. So two fundamental law forces exist in the classical physics, and what it is this field reflects the real physics situation, because the field creation needs some time. So gravity's wave, they talk about gravity wave, the wave come, or Maxwell's equation show that this potential field needs some time to propagate, and so it talk about time required to create a field, and this field interact with another charge. So the field-based interaction and the force, two fundamental forces. Okay, so that's is more accurate and considered as more fundamental. So what's happened? If you have this Newton's law, you can get to the field theory. Well, yes, with additional consideration. If you have a Coulomb's force, you can get the Poisson's equation, yes, with additional consideration. So this is more like we can deduce Coulomb's law from Maxwell's equation, Poisson's equation, and we can deduce this Newton's gravity from this field gravity equation. So what is fundamental here? The fundamental is more like this is fundamental physical law you have to learn, instead of this is just an introduction of what you're going to learn. Okay, so you can go from this one. Actually, historically this came from this one to this, but you can prove this equation from this one. Same way, historically it came from Coulomb's law to Poisson's equation, but using this you can prove Coulomb's force. So it's like whichever is valid, it's going to be both are valid. The situation is like, for example, you learn the Euclid geometry. Euclid geometry in high school. There are two important examples. The important example is about two basic fundamental in the Euclid geometry. Okay, that means you have a parallel line that goes through the point outside of line is going to cross or doesn't cross, or you have more parallel lines than more than one parallel line which doesn't cross to this line. Okay, you assume this is correct, then you can prove that the sum of triangle is 180. On the other hand, if you assume the sum of angle in any triangle is 180, then you can prove this. So either way is fine. Either the one or two can be adopted as a fundamental axiom in the Euclid geometry. So which one we should take it? Well, I think it's Gauss one time take this one and try to prove this using the three mountain and try to measure the angle, and if it's proved, the measurement prove the sum of triangle is 180, then this can be proved, the parallel line axiom. Okay, so it's the same situation here. If this field equation is correct, then it's explained Newton's law or Coulomb's law. And if Newton's law and Coulomb's law are assumed to be fundamental, then we can deduce this field equation with a little bit additional assumption. Okay, so what you're talking about fundamental law in the classical physics, actually Newton's gravity or Coulomb's force, you learn this as a law, but that can be proven by this field fundamental law. Okay, so what's the situation in the fundamental law? In the electromagnetic field theory is Maxwell's equation. This Maxwell's equation is fundamental, but for the force, magnetic field is not essential. What does it mean? Well, if you move the charged particle in the magnetic field, it's get the force. Is a magnetic force? Magnetic field is generating force? It's not. Okay, magnetic field is intermediate field. When the charge move in the magnetic field, that's generate electrical field, and electrical field with a charge generate a force. So what is essential is the electrical force, and interaction between electrical force and the charge is actually same as Coulomb's force. So when you learn Lorentz force, it's actually physically what is fundamental is Coulomb's force. It's not really magnetic field. Magnetic field doesn't generate directly the force. It's just intermediate state field used in the math. Okay? And gravity side, there's nothing like Maxwell's field equation. But Einstein made a progress in here. The Einstein said relativity theory, special relativity theory, is to set the speed limit to the motion. And this was new. In order to set the speed limit, inevitable result is space and time are not independent variable. They are related. Okay? And Maxwell's equation, the R and T are not related. Still they are independent variable. But by Einstein, the R and T are related. So this is nothing to do with gravity things. Okay? It's a space-time relationship. So we have to be able to combine this together with Maxwell. Later, Einstein worked on general theory of relativity, which is about the gravity. Okay, and R and T are related and made a field theory of gravity, just like Maxwell's. Okay, so this general theory of relativity is about gravity, and Maxwell's equation. There are two field theory in the classical physics, and Einstein's dream was to combine them together into a single unified theory. Okay, but it's never happened. So interaction between potential field, and the problem is it's a wave, not particle, because when particle gets small, it's become wave. So we talk about mass to mass. This mass create field, and that will interact with this mass, and force is generated. But when this mass gets small and small, then it's become wave, and that's the boundary of classical physics and new physics. The modern physics is a quantum mechanics. Okay, so small particle is a wave, and that's expressed by the Schrödinger's equation. Wave takes only discrete state. According to this equation, wave is not analog wave. It takes only the discrete, and it's not like analog particle. So because of this, the atomic structure is kind of unique. It's not analog. When you say orbit, it's not arbitrary orbit like moon around Earth or Earth around the sun. There is a nucleus, and there's an orbit. Orbit has only this discrete state. Okay, and between electron and nucleus, is there anything else other than electric force? This nucleus plus and the electron is minus. Well, chemistry confirmed that energy required to remove the electron matches the work required by the electric force. That means no other force is acting on the electric within atom, but it still takes discrete value, and that is something to do with the structure of electron, and it's not by force or energy, and this is called Pauli's exclusion principle. And when physicists say the principle, that means we don't know what it is. You just have to accept it. So honestly, physics doesn't know what the Pauli's exclusion principle, where it's come from. It's just something to do with this discrete state of electron, but it's not exactly understood very well. And within a nuclear force, there are two other forces, strong force and weak force. So we have totally 4 fundamental forces in the physics. Okay? And 2 of them are in the classical physics. And you will learn 2 more in the quantum mechanics. And there's another force called van der Waals force, and our understanding is this is just another form of electrical force. It's just dipole. The molecule create a dipole, and dipole, they attract each other and kind of force. So it's basically same as Coulomb's force. Okay? So boundary between classical physics is here. When you learn the Maxwell's equation and the general theory of relativity, and that's explain everything about 2 forces. Okay? And that's the classical physics. That's what you learn. And beyond that is the quantum mechanics. And you have 2 new forces right now currently understood. And there are more than just the forces. There are a lot of principles, laws, many stuff, because we don't have a good understanding on quantum mechanics at the atomic level. So it's ongoing science right now. Okay, but as long as the first 2 forces concerned, we have very well established theory, which is field theory of gravity and the field theory of electromagnetic field. Okay, so you have to consider Maxwell is the ultimate goal of the classical physics, and also general theory of relativity is the ultimate result of the gravity field theory. Okay, and combining them together has not been performed. That was Einstein's dream, and he worked on this, but he couldn't finish it before he passed away. Okay, so I hope you understand the classical physics, what you learn, and the boundary between classical physics and modern physics. Okay, so I hope you enjoy listening this. Please check other videos, and if you like, click subscribe.